officials of the European Union funding officials.
Excellent. So I will give some introductory words. Okay.
Okay.
And then I have to leave, and then I will connect again in an hour or so.
Okay.
Okay.
You have the.
Yeah.
Go ahead and manage the meeting.
Hello.
Hi, Michael.
Hello, Michael.
Hi, Mike.
Hello, Michael.
Hi.
How are you? Iliada?
Yeah, there are 25 people here.
Okay.
Are you thinking to do a round table at the end of the meeting? Or?
Yeah, we are thinking, with our invited speaker and then with GeoCont colleagues, maybe we can summarize what we did up to now, and then provide some feedbacks related to our project, then closing the workshop.
Okay. Because I will leave for 20 minutes, half an hour, something like that. For you is between, well, it's 9 here, so around 9 here, but I will be back. So for the closing, I will be back for sure.
Okay, no problem.
Okay.
If you want, we can start. Just only
just go ahead.
26 people now attend the meeting. We have 57 registration up to now, but I hope they will join during the workshop. First of all, I would like to thank you. I'm Associate Professor Burcu Saner Okan from Sabancı University. Today, we will have a workshop on the technological advancements in cement additives for renewable and sustainable thermal energy storage in the scope of our European project, GeoCont. GeoCont is mostly focused on the additives used in borehole exchangers in geothermal systems. Today, we will provide some outputs of our project with our colleagues from different companies and different institutes. We have invited speaker for the workshop. First of all, I would like to give the floor Professor Menceloğlu, one of our principal investigator from Turkish side of this GeoCont project. Then we will pass with our director of our Composite Technology Center of Excellence. Then our coordinator will present our workshop and our GeoCont project details. Thank you. Floor is yours, Professor Menceloğlu.
Thank you, Burcu. Thank you, and thank you all for attending this workshop and this dissemination organization. And I'm really happy to be part of this project and very successful and very good team. Actually, it was a very good project we completed. And also I'd like to thank our invited speaker and all you, also the project partners for having talked today, and thank you all of them. And also I'd like to thank the attendees. And I'm not going to take too much of time, and probably Bahattin Hoca will have good presentation about our center, because I do see some of the graduate students and some of the potential students and potential researchers, and it will be very beneficial for you all to knowing about our center, what we are doing here, although it's a new established, maybe 2-3 years already, but we have very good achievement, and I'd like to hear those from the director of our center, Professor Bahattin Koç, and floor is the Professor Koç.
Thank you very much, Hocam and Burcu Hocam, for first of all, bringing this important project to center, and also successfully finishing, almost like finishing this project, and I think this is very important for our center. We are especially with the sustainable environmental manufacturing or like materials. This is very critical for not only for globally, and also it's one of the key areas that the centers actually focus on. Before I would like to take very short time to just give you a brief information about the center. I'm the director of the center. Center is actually called the Sabancı University Integrated Manufacturing Center that was established in 2016, but actively actually the center is operational since 2018. It was funded about like a 35 million US dollars with the different sources. It is one of the unique center where we have the actual production and also research done in the same floor, same building. We have Corsa is one of our partners in terms of the composite manufacturing, composite materials, and also we have other companies actually also our main partners for other areas. Two areas that we focus on: the composite manufacturing. The other one is the additive manufacturing. We have total 150 people actually working at the center currently right now, out of which 13 faculty members from different fields, from material science, mechatronics, the mechanical engineering, manufacturing. And also we have, this is actually very impressive, I think for any center, we have total about 85 students, graduate students, that actually working here, out of which again 60 of them PhD students, which is actually again a very great number. I'm very happy with that one. We have in 2 years we have total 185 publications and 16 patents that actually commonly used. The center also is a hybrid center that's actually again unique in terms of the for all the other centers where we have the very strong academic side as well as the technical side. So we have total 53 engineers, technicians actually working here. We are one of the only 6 university centers with the AS9100 certification for aerospace grade certification, and also ISO 17025. Again, these are unique things compared to other university centers. Actively, we have about 20 million US dollars active projects going on right now. About 55 projects currently, and then we take the Sabancı University. I mean, we are at the Sabancı University. We are very strong in terms of the research for the technology readiness level from 1 to 3. But the center actually takes this a step ahead, more step ahead, and takes the TRL 3 to up to 7, sometimes even 8, to get to the prototyping level. So we have very strong capabilities. If you are interested, in, you can actually look at the website. We can get more details of the center. But if you have any questions, you can send email to me or Burcu or Yusuf Hocam for more details. And again, I would like to thank all of you to attend here, and I welcome everyone. And I would like to very successful workshop, and I'm sure that this project will get a lot of benefits out of this session. Again, thank you for all attending, and I would like to again thank you for all the researchers that makes this project very successful.
More invitation for lunch or dinner?
Always, I'm like I said that like we have to do this one online. I don't like it at all, but I owe you at least more than
project
lunch.
team.
Yeah, so we'll definitely invite you to the Istanbul and the center so that we can get like real celebration of the end of this project. But unfortunately, this time we have to do this online.
Thank you so much, Hocam.
Thank you very much,
for nice
best wishes for
introduction.
the workshops.
And then now I would like to give the floor to our coordinator of GeoCont, Professor Javier. Floor is yours.
Hello.
Hello.
To all of you. I
Hello.
hope you are all well there in Turkey. I hear from Spain. We have done a successful work here within the team with your university also. I would like just to say that shallow geothermal is one of the technologies in which Europe is relying to solve the energy crisis, because geothermal has a very good conditions as a flow of energy. And this investigation, this research about new materials to help to aid the implementation of shallow geothermal energy in Europe is quite important. We have done a successful work with our team, not only in the research about grouting materials, which enhance the thermal contact of the soil of the ground with our systems, with pipes. We have done also research on different aspects on how heat can be stored in the ground. So GeoCont has been a groundbreaking project along 4 years of activity. And today we really are proud to present our first course, in which we are going not only to teach some contents about this research, but also to present and highlight for the first time some of the main results and main activities we have been doing along these last years. So I will thank you very much, Burcu and Yusuf and the rest of the team, Ilaida, and congratulate you for the excellent work we have been doing together. In the case of Savanci, there has been also a groundbreaking research on not only what is the state of the art in thermal transmission, but also what in the future could be groundbreaking, let's say, novelties in the case of how the chemistry of the ground, the chemistry of the grouting of these materials could be improved, enhanced in future with new ideas, which are really very interesting. And there has been a lot of publications and a lot of activity in the, let's say, strictly research domain. I will really congratulate you also for this course, which is the first one, which has been excellently organized, and will be followed up by several others here in Spain, also in Germany and in the Netherlands. So really thank you to all of you, and I hope you have a nice day, a nice attendance, and I will connect again in a while from Spain. It's very early here, and hopefully it will be a nice success. Thank you.
Thank you so much, Javier, for nice compliments. We are really appreciated to work with you and to work with this group, and then I hope we will work together near future in the following calls in Horizon Europe. So we will continue our research in this field. Thank you so much again. Now I will give the floor to our technical manager of GeoCont project, Dr. Jose Manuel Coes Castel. He is also from Spain. Now, floor is yours. Thank you so much for your participation.
Thank you to you, Burcu, for this great organization of the course. It's my pleasure to be here and to present the project, because we consider that it's necessary to do a overall presentation of the project to put all the people in context of what are we doing. And this is my work here. It was a pleasure to collaborate with you. It was great to have this kind of consortium. So hopefully we will be in contact very soon. So I will take the screen. I want to see. Can you see my screen now?
Yes, exactly.
Yes, we do.
Okay, this is the. I will stop video. You see the screen, no?
Yes. No.
Okay.
Perfect.
So this is the first e-learning course. Is focused on the presentation of the project Geocom. My name is Jose Cuevas. As Burju already say, I'm researching in the Polytechnical University of Valencia, and we have the role of project coordinator. So first of all, it's necessary to introduce the project, the Geocom project. That is an European project funded by the European Commission in the framework of the Horizon 2020 program. This is a research program with a lot of projects. Some of those projects will focus on the mitigation of the climate change. So it was selected within the goal of developing the next generation technology of renewable electricity and heating and cooling. Was financed with 4 million euro. That was quite nice amount of money for research. As I state in the name of the project Geocom, is searching for solution to increase the thermal performance of the different elements of the shallow geothermal energy system. So the different elements, the main elements is, related to the ground are the pipes and the grouts that is used for the shallow geothermal system. And the overall cost reduction of about 25% of the main aim of our project, leading to a substantial gain in competitiveness of this typology of system. That is one of the main requests for be competitive in the case of the renewable solutions. Okay, this is the index of my course. So first we will see some main concept in the project Geocom, the general overview, the importance of the consortium and our main objective, then the technical goals that we have, an overview of the main project results. It's just a short overview because you will get more information from the different presentation here, and final conclusions and resume. So in the general overview, I would like to introduce first of all what are the shallow geothermal energy system, because maybe some of you are not aware about what are these systems. So shallow geothermal systems have been widely presented in one of the modules of the course. It's available in the website of the project. So you have opportunity, you can check in the website to see much more detailed information about shallow geothermal system. But I just want to remark some of the main advantages of those systems in comparison with other alternative solutions. So the main advantages, as you see here, is the renewable energy for heating and cooling and domestic hot water associated with heat pumps can be provided by means of these shallow geothermal energy systems. This energy is available 365 24 hours per year, so it's not depending on the climatic condition, it's not depending on the weather, it's just an energy that is stored in the ground. So we have technologies for recover this energy, and it can be combined with other renewable energy sources. So another important aspect is that there are different kind of coupling for this kind of system to the house. But it's clearly dominated, but more than the 90% of the cases, by vertical borehole heat exchanger. Our work have been based on this. So now the next slide show the importance of a robust consortium to perform this kind of project. No? It's very important aspect to be successful achievement of our objective was the design of a strong and robust consortium of the project. Our consortium is multi-country and multidisciplinary, as you can see here. We partner with a vast background in different fields that are key in the project. A first presentation of the partner is here. You see there is the University from Valencia, Aimplat, that is also Spanish, RISE, that is the Swedish Institute of Construction, but it's a Swedish Institute of Research. Savanzi University, of course. Silma is an Italian company, but I have here a more detailed main field of research of the project and key partners. So in the project, we have been working in geothermal energy design and testing of installation, where the University Polytechnical Valencia and UBEC, that is a German company that is with a background in installation of shallow geothermal systems. We have been developing additive for grouting, that is Carmel Olefins and Sabanci University have been leading this research. Sabanci more focused in the carbonaceous particle, and Carmel Olefins more focused in phase change material, as you will see later in the presentation. Then we had the development of a new generation of growing products. These have been led by the Research Institute of Sweden, by RISE, and with the key participation of Cinsa, the Cinsa Cement, is a Turkish company, because they are the industrial partner to prepare all these kind of grout, new grout with the new additives that have been performing before. And finally, we have the development of the new thermally enhanced plastic heat exchangers, have been leading by Aimplat, that is a research institute in Spain, and Caudal and Sigma, that are two companies. So you see here, the involved countries are Spain, Sweden, Germany. Sorry, I don't know how to go back. Well, Turkey, Italy, and Israel. So the technical goals of the GEOCOM main objective, you can see here all the technical goals that have been listed in the project. It's part of the unit 2 of this core, and then the main objective of our project could be listed, as you can see. In resume, we could group objective related to the enhancement of the plastic pipe by means of optimizing his thermal and mechanical property to guarantee a better performance. This could also consider the optimization of the geometrical configuration of the heat exchanger that play a fundamental role on the efficiency of the systems, according to our observation and other papers. So the geometrical configuration together with the new products are enhancing a lot the performance of the plastic pipe. Then we have two objectives for developing new additives for modifying the property of the growing product. One of those additives, the carbonaceous particles that have been developed by you, produce an increment in the thermal conductivity of the grout, whereas the other, the PCMs, increase drastically the thermal storage capacity of the grout and the modulation of the temperature in the ground, because it can store the energy. With those additives, we had the goal of producing tailor-made performance groutings, adapting to formulation for the different European geological settings. If finally, the development of a tool for deciphering the optimal combination, considering not only the performance, but also the LCA. So the first technological objective of the project is the enhancement of the current pipe uses a heat exchanger. The vertical heat exchanger are generally made of P100. P100 is the plastic compound. The mechanical property of this product fulfill the performance of the shallow. Sorry, I don't know why, but this is passing automatically. Just a second. I don't know why it's passing this automatically. Let's see now. So as I say, the development of the plastic pipe, the mechanical property of the product fulfill the performance for shallow geothermal system, but has some limitation in terms of thermal conductivity. In our project, we have developed very similar compounds with enhanced thermal conductivity and also the mechanical property that fulfill the requirements. Then the second part is the additive for grouting that have been also taken in the project. The objective of the new additive were to increment the performance of the groutings by means of decreasing the borehole thermal resistance. This is a key parameter for controlling the performance of the systems. Increase the thermal capacity and increase the energy heat storage. The products should be compatible with cementitious grout with a specific formulation and mixing procedures. The simulation for deciphering the optimal performance have been done, and then we in the most of the geological setting around Europe, that is also similar in Turkey and other countries, shows that the thermal conductivity of the ground should be between 2.5 and 3 baht per meter cube being. Then the combination of the innovative solution, all these combination, including the pipe and the grout, will deal to the production of this tailor-made solution for grouting. So will be responsible for the significant reduction of the total length, up to 20% of the borehole field associated to the shallow geothermal system. It represents an important saving in the installation phase of the system, and at the same time, a compelling enhancement of the performance of the system during its life cycle. So it's not only that you are reducing the price during the installation, but also you get a better performance, energetic performance of the system during all the life of the installation. That is, considering that the standard life of this system are for 25 to 50 years, it means a lot. So the next thing that I would like to show in the Unit 3, the overview, the main project result, as you see here in the list. And so the two first is part of our course today. So the carbonaceous additive for enhancing thermal property and the shape stable PCN will be presented later on by my colleagues in detail. Then new plastic pipe with enhanced thermal property, design of optimal geometrical configuration for the heat exchangers, grouting with enhanced thermal property fulfilling the requirement standard. All those results have been tested in relevant environment in different locations. So we can say now that we have been installing this in Valencia. It's a test site in Valencia with 7 different configuration of boreholes. We have installed it also in Sweden, where the PCN have been tested. It's a very innovative work, because the PCN have been used in a lot. PCN have been used in a lot of application, but never in the field of the shallow geothermal system. So we are really innovating in this aspect. And then we are currently installing the 2 different systems in Germany in a real installation for a house. Well, it's not really a house, but it's a building. So in all these test sites, we are testing all our advances. So we have testing this additive, the grouts that have been performed, and also the pipes, and the new configuration that have been created in the project. So I will just go to the next slide, but very shortly, because they will be presented later by my colleague.
Okay, can you go to presentation mode?
Yeah.
Okay.
I don't know why, but it's automatically passing the the slides, so I need to stop a little bit. Okay, this is the carbonaceous additive for enhancing the thermal property of the grout. Savanchi has led this activity, and I'm sure that you'll be presenting this result much better than me. So it has been created in order to increase the thermal conductivity of the grout, and also at the same time is reducing the borehole heat, the borehole resistance, that is key for determining the efficiency of the system in the future. So the next thing that will be presented also today with the Carmel Olefins, the Basan group, have been developing a new generation of shape stable PCN with capacity to be introduced into the ground in order to increase the thermal capacity of the grout for buffering the thermal demand or increasing the storage heat. As I said before, depending on the application, we can get a buffering effect, or we can increase the storage heat capacity. That is very important for district heating, for instance. PCN are particles that can store heat during the transition between solid and liquid stage, and those could be literally afterward in order to buffer the energy demand. So the next thing is the new plastic pipe with enhanced thermal properties that I will escape again, because in other case it will pass. The preparation of the master batches was done by Spinpet and Silma, that is an Italian company, avoiding the development of different formulations that were used for producing a small amount of compounds. Those compounds were characterized and the best formulation were selected for the final production of thermally enhanced pipe that have been tested in the test site. The mechanical properties are similar to standard P100, and the thermal property are widely better. We are talking about thermal property around 1 baht per metric Kelvin when the standard is 0.44 42 more or less. So we are more than doubling the current value of the thermal property. The produced pipe were tested in Valencia, showing very good result, and now we are installing in Germany, as I say, with different configurations, single U, double U, coaxial configuration, etc. So we are very happy and very proud of this result, because in general the installation can be really enhanced with the combination of the different solutions. Then the design of the optimal geometrical configuration, as I said, is not a question, it's not a matter only of the plastic compound, but also how do you distribute these compounds. We have made an optimization of the geometry of the heat exchanger, and this look like with different simulation tools, no? And it look like the best solution would be something like this kind of coaxial system, let's say coaxial system, where you have a central pipe and 3 outer pipe with different thermal conductivity. So the central pipe is quite isolated, whereas the outer pipe are with a high thermal conductivity. So it's increasing the heat exchange between the pipe system, the borehole, and the grout. Especially when this green color means the grouting that we have been preparing with all these particles, as I said, with a very high performance. So the next slide show some slide result of the grouting with enhanced thermal properties. So all these particles that have been created by Savanchi and by Carmel have been used to prepare new grout together with the cement from Chinsa, and we have different solutions, and the most important is the thermal conductivity, as I say, because you can see here that we are talking about thermal conductivity achieved with value around 2.9, 2.7, that is in the range of the best performance for this shallow geothermal system. So in Valencia mix, in the real field test, we achieve a thermal conductivity to about 2.7, whereas the standard product that are used in the field claim for thermal conductivity about 2, and the reality is that the thermal conductivity of those products in the field is around 1.7, 1.8. So we are really enhancing this. So some final conclusion and resume before you go to the detail of the different presentation that my colleague will do, is that the project geocom objective will trigger a significant enhancement for the shallow geothermal sector by means of optimizing different elements with a role in the performance of the system. As I say, these elements are the pipes and the grout mainly, but in the pipes, as I say, the compound, the configuration, the additive, all these parts have been the work. Our project goals were established in concordance with the simulation and modeling tools that are widely used in the market. So we tested in the model, what could be the result if we obtain a product with this configuration, and we saw that the result at the end of the day, the result of this simulation for shallow geothermal system give you a total number of meters that have to be drilled, no, and installed. So for instance, you have a standard house with 150 square meters, something like that, you will get something like you need 150 meters of drilling for heating and cooling your house. But if you put this, you can decrease this length by 20%, 20-25%. That is the most important achieve that we have done. But also, you increase the thermal performance of your system, that is measured by a coefficient that is called coefficient of performance of the system also. So at the end, you will get saving in energy compared with a standard solution. So those results or goals have been achieved and tested in different scales, showing very fruitful results, as I say, in Valencia, Boras, and now in Germany. And the validation and real scale of our result allowed to establish some strategies for the future exploitation of resource and enhancement of the shallow geothermal system. So now we are dealing with some part of how to explore this resource, not only in the commercial part, but also in the scientific work. That I'm very proud to say that some of your colleagues have been doing the thesis with some of the research that you have been doing, Burju, Ilaida, I guess. And this is, in resume, this is in conclusion, this is all from my side. I really want to thank again for giving this opportunity to present the project, and I wish you a very, very fruitful workshop. And I will be here. I need to leave, as I say, I need to leave for a while, but I will be here around 9:30 here. This is around 11:30 for you. Thank you very much.
Thank you so much, Jose. This is very informative introduction of our GeoCon project. Maybe in the round table there will be questions related to a project. So maybe we will take the questions in the round table if it is suitable from your side.
Yeah. I will be here. I will be here for the round table for sure.
Okay. Thank you. Now we will go with the next presentation, our site, Sabancı University site. So, Jose, maybe you can turn off your screen.
Yes. Yeah, Jose, you need to stop the screen sharing.
No, I couldn't
Yeah.
find it.
Okay,
So
okay.
I couldn't find the button. It was moving.
Okay, thank you so much again. Now, my turn. At this time, Sabancı University team is going to present our outputs during GeoCon project. Maybe I can turn on my.
Turn your microphones off.
I turn. Okay. Now, yeah, I'm confused. I turn on my camera. Turn off my camera now. In the Sabancı team, we work together with İlayda. Also, she is our project engineer, and then also graduate student, and then she also graduated and successfully completed our master program at Sabancı University from Material Science and Engineering Department. We I think published we published 2 papers and then submitted 1 paper related to our part, and also we carried out this research with Professor Menceloğlu during this 3.5 years of this project. In our part, we mostly focus on the carbon-based hybrid additives, and then we try to understand the different sources and then investigated the virgin and waste sources to enhance the thermal conductivity of the grouts. Yeah, as you know that in the recent years, energy demand is growing interest for whole world, and people are looking for the alternative solution to get high energy efficiency. Yeah, as you see, this is the distribution of the total primary energy demand of the world, and then geothermal energy is one of the popular ones. And getting increased, and then this is very important related to geographical conditions and the water source regarding the location, and then other alternative energy tools are going to develop by our country, also the rest of the world. Yeah, especially when we look at the shallow borehole exchangers, this is the schematic representation of the one of the geothermal energy system. As you see, there are pipes and then also grass covering these pipes. And here it is important to get high, to preserve the heat inside. So therefore you need to manage the thermal conductivity of the pipes and the grass that they are using. Yes, there are some commercial grass available and then used in these commercial systems, but in that project we try to achieve highest thermal conductivity and then highest efficiency, and then also we address the waste sources by decreasing the cost of the grass used in these systems. And then when we look at the importance of the thermal conductivity in grass, yeah, there are several parameters like you need to adjust the water content and the density of the constituents and the type of the carbon material that you choose and the particle size of the carbon materials, and then how you incorporate these materials in the grass. And if you increase the also thermal conductivity of this system, you can also decrease the length of these pipes and then heat exchanger. This is another advantage of this output. In the literature, also in the market, there are several attempts related to increase the thermal conductivity of the grass. Yes, there are some nanomaterials widely used like carbon nanotubes and graphene. Also, graphite is also used in previous European projects. So therefore, in that project, we focus on the graphite and graphite-based structures. Sorry, and then also we develop the bentonite and cement-based grout to increase the thermal conductivity. Yeah, there are some problems for grout development, like high water uptake, and then also the surface chemistry of the additives that you developed. Yeah, you have to improve the interfacial interaction among the constituents in the grout mixes. And if you do not manage the distribution and dispersion of these additives and then constituents, there will be agglomeration and the low dispersion. Also, this also negatively affect the thermal conductivity and decrease the thermal conductivity. In this project, we focus on the new solutions, and then we try to control the grout chemistry and then water demand by developing new formulations. And also we modified carbon surface by salinization route and developing hybrid nano and micron scale particles to enhance the thermal conductivity. In the scope of the project, we mainly focus on three different materials, three different carbon sources. One is the graphene nanoplatelet. This material is produced from nanographene. I'm one of the co-founder of nanographene company. We are producing this graphene from Vestager. Therefore, we choose this material because, as you know, that the circular economy and the sustainability are important issues discussed in European side and also in around the world to use waste sources and convert them into value-added materials. Another material we choose is expanded graphite. This is different from the graphite flake used previously in the previous European project. And then we especially focus on the particle size and then try to find suitable expanded graphite for our grout formulation. And the last one, also this is the very interesting one, is rice husk ash. We obtain this material from Valencia, and then this also can be used as an additive in grout materials. First of all, I would like to give a brief information about graphene. Yeah, graphene, as you know, that discovered in 2004, and then this material was investigated by the group from Manchester University, and then this group also received Nobel Prize in the field of physics in 2010, and there are many applications related to the utilization of graphene, like in automotive, in retardant materials, in construction industry, as we discussed now, and also batteries, textiles, and wind turbines. And then there are it has outstanding property like mechanical performance, thermal properties, electrical conductivity, and flame retardancy. So people, researchers and scientists, and then people from the companies are started to focus on the development of graphene related materials and products. And there are some difficulties in mass production of graphene. As you know, that people are mostly used highly oxidizing agents, and then also during the oxidation of the graphite, it can be exothermic reaction, so it's not easy to tailor the reaction conditions, and also it's not easy to control the surface chemistry and the number of the layers and the particle size during graphene and graphene oxide production in this process. And also this is when you increase the scale, it's not easy to handle this kind of toxic materials, so you have to increase your precautions. Therefore, these are the main barriers in the scaling up of this material. What we do in 2013, I received investment from TÜBİTAK to continue and develop some formulation to get graphene from waste sources. We received different sources from different parts, like lemonade peels, peels, and other carbon waste. And in the end, we focus on waste tire sources, and then after pyrolysis of waste tire, you can get some recycled carbon, and we use this recycled carbon as a starting material and apply some upcycling process, and to get graphene nanoplatelets. As you see that the graphene nanoplatelets that we have has some surface oxygen functional groups. This is really important because you can manage the interfacial interaction and then control the hydrophilicity during the integration of this material into the selected systems. And that the particle size is around 50 nanometer. And when we look at the expanded graphite compared to graphene, and then this is the highest quality and then expensive one, but graphene from waste tire is cheaper than expanded graphite. So we try to see the performance in the grout systems. For expanded graphite, we obtained from SGL company, which is one of the carbon producer in Germany. And as you see, this expanded graphite has a 2% oxygen group inside and highly crystalline material, and then contain several graphene layers inside. And in order to activate these carbon surfaces, we developed some synthesis route for selenization. Therefore, we use this amino-based silane coupling agent, widely named as APTES, and we apply some hydrolysis process with the interaction with the silica particles, and then we produce uptase functionalized silica particles to make hybridization with the selected carbon materials. As you see, this is a functionalized silica, and in the hybridization process, this can be graphene, graphite, or other alternative sources, and then you can make the bridges with these Slane coupling agents. And then you can increase the interaction with the help of these silica particles with the matrix, grout matrix, since it also contains silica particles. So this also provide harmony in the system. We conducted optimization study for functionalization of silica, and then we changed the Slane coupling agent concentration. I don't want to go the details, but we try to find the optimum ratio, optimum amount to functionalize silica, and then we check the chemical surface properties, and then carbon, oxygen, silicon, and nitrogen ratio to understand the attachment of the amine groups coming from the Slane coupling agent. And then we choose one type of the additive, and then continue with this material for the hybridization process. First, we hybridized with this silica functionalized material with graphene from Vestager. Yeah, graphene contains functional groups, oxygen functional groups, and then there is no need additional treatment on its surface. So we directly hybridize this material with different ratio of this silica functionalized silica in just only water medium, and then to observe the thermal degradation and surface chemistry changes by the by two types of concentration. And then we also confirmed the structural formation and this hybridization with different spectroscopic and microscopic techniques. Then, with the colleagues from Rice and Chimsa, we developed grouts by the addition of our hybrid materials by taking into consideration the reference material. So we try to control the water demand, and also we try to adjust the other constituents like silica sand and the cement and bentonite contents, and then we try to keep them constant, and then to see the properties of the material, and then to see the behavior in grouting of this material. And then as you see that the water content directly affect the thermal conductivity. And for example, when we look at our reference, we need just only 650 gram water, but when you add hybrid materials with 5%, your water demand increase. But when you change the carbon content in your hybrid, we observe that when we increase the graphene content in the hybrid material, we can decrease the water content, and then we can increase the thermal conductivity. So this is the really good funding to observe the hybrid composition, the effect of the hybrid composition on the thermal conductivity. In this second one, in expanded graphite, also we perform similar characterization techniques like graphene nanoplatelets, and then we altered the functionalized silica ratio in the hybrid structure, and then developed different types of, especially two types of hybrid additive with different silica content. And then as you see, the surface area directly changed by changing silica content and increasing carbon content. And also we confirmed the structural formation by Raman spectroscopy and TGA, and also microscopic studies. And then we also check the thermal conductivity of this hybrid system. So again, we observed the importance of water demand, and then also the amount of the carbon content in hybrid structure. And as you see, when you increase the hybrid additive up to 5 weight% in the grout mix, so we can increase the thermal conductivity up to 2.6. So this is important for us. Yeah, this is very schematic, systematic process. So in the application side, in the pilot scale side, we just only focus on the neat expanded graphite. Yeah, there are also we try to develop mild synthesis route for scaling up this kind of hybrids, and then increase the technological readiness level. And the last material that we worked is rice husk ash. Rice husk was exposed to calcination, and then it converted to ash form, and it naturally contains silica particles. As you see, when you look at the TM images, we can clearly see silica nanoparticles on the carbon sheet surfaces. And then the particle size is around 4 nanometer. And then in that part, we don't have to apply any attachment of silica particles or on carbon surface. And we also directly use this additive. Also, we try to increase the interaction with the constituents of grout, and then we applied additional functionalization process to observe the interactions. And then this is highly porous structure. Also, we deducted from SEM characterization. This is a schematic reaction related to rice husk ash functionalization by Slane coupling agent. The same methodology was applied first. Slane coupling agent exposed to hydrolysis process, and then we turned into OH groups, and then these Slane coupling agents interact with the calcium silicate hydrate of rice husk ash, and we functionalize the surface of this material. And then again, we control the surface chemistry and the thermal degradation behavior of this material, and then confirm the successful functionalization. And then we check the thermal conductivity. Yes, when we look at the results compared to expanded graphite and rice husk graphene nanoplatelets, the thermal conductivity values are a little bit lower, but this carries potential because of the circular economy issues, and then this value added weights can be reused for this kind of applications. So we try to understand its behavior in grout mix, and then by the addition superplasticizer, bentonite material, and silica sand. And then we again develop some formulation with the colleagues from Chimsa and Rice. I want to conclude my part. In GeoCont, we try to understand the importance of the carbon additives obtained from waste sources and virgin sources. And then we try to get the highest thermal conductivity, and then try to reduce the manufacturing cost, and produce these hybrid materials in a mild way, and then trying to reduce the obstacles faced in the production of this kind of nano-based and or micron-based value-added materials. And also we performed pilot tests in Valencia and in Germany with the colleagues, and then we also got successful results, as also our technical manager mentioned some results related to our GeoCont project. I would like to thank you to my colleagues and then our Sabancı team, Çimsa company from Turkey, and then we did a great job together. Thank you so much. If you have any question, I will be happy to answer, and then you can also send an email to me. Thank you. Okay, and now we can, if you want, we can give 5-minute breaks and then continue with the next speeches. And during the break, I would like to show the video of our center, so then we can also take our coffees and then come again. Thank you so much.
Cortsa operates in a wide geography from America to Asia Pacific. Today, we reinforce 1 of every 3 car tires and 2 of every 3 aircraft tires globally in the tire reinforcement industry. We started our operations in composite industry by translating our 45-year know-how in tire reinforcement business. Composite Technology Center of Excellence is launched in 2016. It is where we develop composite materials and technologies for the automotive and aerospace industries and export to many countries across the globe.
Established as a result of collaboration between Cortsa and Sabancı University, the center focuses on technology development, covering the entire value chain in the areas of composite and additive manufacturing. Actually, what we are talking about here is a technology hub where all the stakeholders, namely students, designers, engineers, researchers, faculty members, managers, and entrepreneurs can work within the same environment. Being the 3rd campus of the Sabancı University, graduate students can take their courses and at the same time perform their researches in the field of manufacturing, material science, and mechatronics while utilizing the state-of-the-art infrastructure at the center.
In accordance with the product demands from our customer, a project or working team is formed. Our team uses necessary design and analysis tools or software considering the geometry of the workpiece, its expected features such as strength, weight, flammability, its working environment requirements, and other essential features. Then, we cut the prepregs or fabrics in required shapes and sizes for composite production under clean room environment conditions. The cut preforms are laid onto molds and then vacuum bagged. An indispensable method of production mainly used in aerospace industry is the automated fiber placement. Using this technology, we can produce repeatable and more reliable composite parts with robotic technologies, eliminating human error. Depending on the application intended, the preform is cured in a pressure, heat, and vacuum-controlled environment using oven, press, or autoclave, and hence transforming it into composite product. That the molded composite part is trimmed or machined to its final shape if relevant. The manufactured parts are subjected to detailed quality controls through using appropriate characterization methods, destructive and non-destructive testing. If the test results meet the requirements, part production process is completed.
Fabrics, prepregs, and sandwich panels used in aircraft interiors are produced in our AS9100 certified production facility. In Composite Technologies Center of Excellence, we have created an open innovation habitat, and we invite all stakeholders and universities working on composite technologies to benefit from this one-of-a-kind innovation zone.
Now we can continue with our next speaker. Next speaker is Dr. Michael Schuster from Israel, from Carmel Olefins company. He received his BS degree in chemical technology, and also his PhD degree from macromolecular chemistry, and then now he's working in Carmel Olefins. And in our GeoCon project, he and his team developed phase change materials to be used in grout formulations. Now the floor is yours, Michael. Thank you so much for your participation.
Thank you. So, hello everybody. My name is Michael Schuster, as you have already heard. I am a researcher in Research and Development Department of Carmel Olefins. And the Carmel Olefins is an industrial petrochemical company located in Israel. Our company produces polyolefins, hundreds of thousands of tons of low-density polyethylene and polypropylene annually, some 250 kilotons of polyethylene and some 450 kilotons of polypropylene. Our Research and Development Department is involved in the developing of new polyolefin grades, and the area of our interest and expertise is polymer engineering and science. And today's topic lies quite in this area. So here I will stop my video and will start sharing my screen. Here it is. Okay, so within a GeoCon project, our company was tasked with developing new novel phase change material to be used as an additive, allowing increase in grout's heat storage capacity.
Michael, can you share your screen?
I'm not sharing?
No. There is a button in the bottom part of the screen.
Just a moment. Sound. Share, just a moment.
There is an icon share screen, yeah. No.
Here, okay.
Yeah, now, yeah.
Okay, now I'm trying to enter slideshow.
Okay,
yeah?
Thank you.
Okay?
No, great.
Okay, great. So, we were tasked developing novel phase change materials. So, I will introduce phase change material, how it works.
Michael, there is a problem in your voice.
What is my voice?
Now is better.
Okay, now it's on maximum now.
Okay, it's okay.
So, so with the focus on organic phase change material, we will talk a little bit about shape stability of these materials, about ways of imparting this important property, and challenges to be overcome on developing this. Then we will discuss the materials engineering concept actually applied in development of shape stable PCM for geocond aspect, for geocond project, and concern in engineering of such materials, and some results. So as you have already heard, geocond assumes that improving performance of shallow geothermal energy systems requires combination of different material solutions for pipes and for groutings. Accordingly, its objectives include development of new groutings with enhanced thermal properties, namely thermal conductivity, which was described nicely by Burcu, and higher heat storage capacity. So if thermal conductivity was achieved via using carbonous additives, heat storage capacity should be achieved via use of phase change materials. Now, reasons for improvement of performance of borehole exchange with improving of their thermal conductivity is quite clear. In order for heat to be effectively exchanged between the heat exchanger and the ground, the heat should easily move out of the heat exchanger and towards heat exchanger. Regarding improving heat storage capacity, it is not so obvious why should it improve the performance of the whole system. Nevertheless, model and experimental studies suggest that in some cases, in some shallow geothermal energy systems, the efficiency can be improved also with enhancement of the grout heat storage capacity via use of PCM. And it is not so obvious. And here we see the excerpts from the study, from theoretical study from 1996, predicted that incorporation of PCM having properly tailored thermal diffusivity into a ground thermal into the ground coupled heat exchanger should result in significant improvement of its thermal performance. Actually, the study showed also that improperly designed PCM reduces the performance. More recent studies confirmed both these predictions. Some papers implicitly suggest that proper use of PCM in the growth of shallow geothermal boreholes may result in reduction of the required borehole lengths, which is a very desirable result, significantly reducing the cost of installing these systems. So what is PCM? PCM stands for phase change materials, and belonging to this group are materials changing their state from solid to liquid, or changing between two different solid crystallization states, over a defined temperature range, phase transition. In order to be useful for thermotechnical applications, this process should be reversible, reproducible phase transition should be, and this process should have significant thermal effect. Changing state from liquid to gas is also phase transition, which can be reversible and have large thermal effect. However, this transition is usually accompanied with a significant change of volume and is more difficult for use in technical applications. In practice, the mostly used phase change materials are actually crystalline materials with high latent heat of phase transitions. There are different families of phase change material, different their chemical nature. They can be organic, inorganic, and tactic. Each family has its advantages and drawbacks, and the relevant for us are organic phase change materials, which are highly crystalline compounds covering a broad range of melting crystallization temperatures and having latent heat of their transitions close to 200 joule per gram. More specifically, for this project, we used organic PCM. So, how does PCM work? PCM stores thermal energy in the form of latent heat of phase transition. Schematically, if we start heating, supplying thermal energy to a solid crystalline material, its temperature will first rise, reflecting the thermal energy is being stored within the solid as a sensible heat. At some point, we continue supplying heat, we continue heating the material, but the temperature will stop rising, and material will start melting. During this process, the temperature will not rise, but the heat will be continuous to be stored, but now as a latent heat. After completing of the melting, we'll get liquid, so the crystalline solid will turn to amorphous liquid, and the heat needed for this transition will be stored inside the system. If we continue heating, the temperature of the material will resume to going up, reflecting again heat stored inside the system again as a sensible heat, but the sensible heat in the liquid. But the process is reversible, so if now we start cooling the amorphous liquid, its temperature starts going down. At some point, it will start crystallize, and the temperature will stay almost constant. And at this point, the heat will be released as a heat of crystallization, and the material will turn back to crystalline solid, and the process can be reversed more and more times. Ideally, melting and crystallization temperatures should be the same, and when the phase transition starts, the temperature should stay constant. In reality, organic PCM usually show melting temperature a little bit higher than crystallization one because of so-called overcooling, and there are small temperature changes during the observed phase transitions. Early in the process of developing phase change materials for practical use and commercialization, it became clear that in order to be applicable, PCM leakage after solid-liquid transition should be prevented. After the material changed state from solid to liquid, it starts flow and it can leak from the place it should be. And there were search and studies how to impart the protocol as a shape stability. And the two main practical solutions are incorporation of PCM within a polymer matrix, giving rise for producing so-called composite PCM. Here we see this crystalline PCM within the polymer matrix, or encapsulation, that is enveloping of crystalline of PCM with the solid shell, polymer or inorganic shell. And both solutions allows to material to undergo phase transition of PCM inside the shell or matrix to go from solid to liquid, but the whole system keeps its geometry and dimensions, which is called shape stability. And in some reviews, it was actually signed and mentioned that availability of commercial PCM, composite materials, and encapsulated PCM is crucial to development and commercialization of PCM applications. It should be said here that imparting shape stability via immobilization within either matrix or within the shell comes at the expense of PCM thermal effectiveness. However, it is highly desirable to get the shape stability to be convenient in technical uses. And here comes Carmel Olefins. Having experience and expertise in polymer engineering, Carmel Olefins has developed a novel concept allowing cost-effective, recyclable, shape-stable phase change materials in granulated or shaped form to be manufactured using conventional plastic compounding equipment. The challenge was finding a way to achieve the desired balance of properties while increasing PCM content to above 70%. The concept was first validated in domestic hot water applications. However, it allows designing materials suitable for various thermal energy storage applications. Specifically for shallow geothermal energy applications, the concept required modification of the material composition, manufacturing equipment, and the procedure. The forms in which shape-stable PCM of Carmel Olefins can be produced include filament form, granulated form, or compression molded plaques. Shape instability of PCM can be illustrated by a simple comparative experiment. If we'll take a classic organic PCM, pelletized paraffin wax with melting point temperature about 60 degrees, and we put granules in the hot water at the temperature of about 80 degrees, the pellets having density lower than the density of water will float on the surface, gradually melting. At some point, finally, a layer of molten powder will form on the surface of the water. viscosity of this molten paraffin is quite low, similar to that of viscosity of vegetable oils. And using such material in technical applications is quite problematic because of its tendency to leak out. On the other hand, if we'll take a pelletized or shape-stable PCM containing about 80% of the same paraffin wax, and we'll put it into the boiling water. Here the water is boiling. We will see that the pellets stay pellets, the plaque will stay plaque, both keeping their geometry and size, despite the paraffin undergoing phase-changing material and changing in state from solid to liquid. The cost of imparting the shape stability is about 20% reduction in the thermal energy storage capacity. Latent heat of this material is lower than latent heat of pure wax. Concepts of engineering shape-stable PCM. Our shape-stable materials are multi-component materials, and considerations of comfort in their engineering are application-specific and include selection of the components and optimization of the composition. The thermal energy storing component should have required transition temperature and latent heat. The matrix should be selected or engineered to provide processability, shape and thermal and chemical stability, and it should retain maximum PCM maximum as much as possible. We use additives facilitating processability of the material and providing required additional properties such as mechanical strength, density, thermal conductivity, and so on. All the components should be compatible with each other and should properly interact to form in situ required morphology and structure. And the final composition should provide the required balance of thermal properties, processability, shape stability, and mechanical strength. So these were aspects of concern during engineering of the PCM. Now, our materials produced using conventional polymer compounding equipment. The equipment should allow convenient and stable feeding of all the various components, their proper dispersion and homogenization, effective cooling and pelletization of the final composition. So barrel and screw of compounder should be properly configured, and the auxiliary devices like feeders, chillers, pelletizers should be properly adapted. The process considerations of concern in developing PCM production process include physical form of the components to feed, feeding order, compounding conditions, pelletization type and conditions. And finally, the process should allow facile, easy manufacturing of shape-stable PCM with good mechanical properties at maximum possible loading of thermal energy storing component. For production of our PCM, we use conventional laboratory twin screw compounder. Before I start the clip, it is quite noisy, so it will be maybe difficult to explain what you can see. But here we see the final part of compounder. We see die with a single hole. We see molten polymer composition exiting the hole, entering the cooling bath, going through the cooling bath, solidifying, and finally entering the pelletization facility. So now I will start the clip, hoping that it will. Yeah. Okay, so this way we can produce up to 4 or 5 kilograms of pelletized material per hour. We can stop on producing filament without pelletizing. Our partners from Sweden spent quite significant efforts and energy developing composition of grout, which can incorporate our material. And the results of this effort you can see here on comparison of phase change material before introducing into the grout and after. And what we can see that the shape and size of granules of the PCM are kept. We see the granules uniformly distributed more or less throughout the grout and interacting. We see no clusters. On the cut surface of the same grout, we can see some more indications of good work done by our partners. We see the particles incorporated into the grout. We see not much detachment of the organic particle from inorganic matrix, implying good interaction. You should understand that these particles within this grout and survived contact with quite aggressive components of the cementitious grout, very alkaline media or medium, and they stay inside the matrix even after cutting it and transporting it. So implying that there is a good thermal contact of PCM with the grout. This way, the PCM demonstrated its chemical resistance, shape stability, and sufficient mechanical strength. And indeed, preliminary tests performed by RISES in Sweden showed thermal activity of the PCM within growths, and the experiments are still ongoing. And here we came to a close of the presentation, and thank you very much for your attention. That's it.
Thank you so much, Michael, for your nice and informative presentation. If any question from audience, we can take 1 or 2 questions. Okay. Now, thank you, Michael, again. And we can proceed our next speaker from Çimsa company, Miss Ayten. And Ayten Çaputçu received BS degree from geological engineering, and also she is a PhD student at Mersin University, and also she is working as a research and development specialist in Çimsa. Now, floor is yours. He is also our end user They are also our end user in GeoCon project, and then they will give some informative information about the utilization of this kind of grouse in cement industry. Thank you so much. Floor is yours.
Thank you, Burcu. I want to say hi, everyone, and I wish to a very healthy and more closed meetings full year. And I'm Ayten Çaputçu from Çimsa Cement in Turkey. Today, I can see that there is some students in our workshop, so I would prefer to give some basic informations about the shallow geothermal systems and the grouts. And then I want to talk about little marketing potential of the grouts and the cement hopes about the future of this type of energy systems. Let me start share my screen. Could you see?
Yes. Yes.
Okay. Okay. While starting, I want to talk about from Çimsa and the mother company Sabancı Holding, and then I will inform you about the shallow geothermal systems. Sabancı Holding, as you know, is a mother company, and the Çimsa is one of the members of this company. I know Sabancı Holding has 26 group companies, and Sabancı Holding has employees more than 50,000, and all holding companies operating 13 countries all over the world. And Çimsa is the member of this mother company. Çimsa produced the 10% of gray cement in all over the Turkey. World's second biggest white cement capacity we have. World's top exporter for cement white cement capacity. And only producer white cement, gray cement, and calcium aluminate cement in one plant in Mersin. And the first and only member of the World Sustainable Development Cement Sustainable Initiative from Turkey. Yeah, Çimsa operates 5 plants in Turkey. Sorry, there's something wrong. Okay. Yeah, Çimsa operates 5 plants in Turkey, Mersin, Eskişehir, Kayseri, Niğde, and Afyon. These are full capacity cement plants. And we have some terminals in Spain, Italy, Germany, Romania, Russia. So we operate all over the world. And Çimsa has the first and only R&D center applied by my ministry. And we have now 4 ongoing Horizon 2020 projects. And GeoCont is the first of them. And it's very important for me because the GeoCont is my first project in Çimsa. So I will be more happy than other colleagues because it's my first project. So why this project we need to do? Because as you know, 75% of the European building stock is energy is inefficient. This means these buildings have untapped potential for renewable energy and energy efficiency. So we can say that there's huge potential to use their untapped potential again. So shallow geothermal energy system is stable, reliable, and renewable energy sources, which protect the nature while you compare with the other systems. The thermal conductivity of the grout backfilling boreholes and pipes has been considered as an important issue for the improvement of the efficiency of geothermal systems. And Çimsa and RISE are responsible for the develop the thermally conductive grouts for this project. And I think our second workshop, which will be held by RISE on 22 January, RISE team will be explain more detail about our grout. So, food project aims to help buildings benefit from the more energy efficiency while reducing carbon dioxide emissions, and it helps to try to protect nature. So, how does system work? We know that shallow geothermal systems use the temperature underground. So, because you can find it all literature, there is some stable temperature underground, and it's independence in the climatic conditions on surface. So in winter, underground temperature is warmer than your surface temperature, and opposite for in the summer. So when winter conditions, your shallow geothermal system pipes and the grounds will take the energy from the underground, then switch them off for heat to your house, and opposite for the summer conditions. So how to improve this system's performance? The performance and efficiency of the geothermal system depends strongly on the understanding control conditions, some parameters. These are some geological conditions, building topologies of the city, and the heating cooling solutions. If you want to use your shallow geothermal system more efficiently, some teams will be point out that these parameters detailedly. For example, you can see the thermal conductivity of the lithology around Europe. Mr. Burkhardt will prepare this map, and you can find his lots of literature paper about the subject. So if you can see the map, you can understand that the average thermal conductivity of lithology is changed between 1.2 to 2. So if you use a grout for these systems, this grout has the nearly same thermal conductive capacity with these lithological parameters. So system life cycles. As you know, we all use central air conditioning system or conventional furnace in our house and the other buildings. But if we talk about geothermal heat pumps, they serve us 20 to 25 years life cycle. And geothermal ground loops has the life cycle more than 50 years. This means you will set your system one time and then you are relaxed. Advantages of the shallow geothermal systems. This means I'm talking about the systems and which include all the pipes and grouts in it, because you know it's whole system work together. These systems helps to save up to 70% and heating and cooling cost over conventional systems. And as we see in our Valencia application, I think it's 22% for heating reduced cost conditions. The system is available for 24 hours and all year. There's no, you don't need to turn it off or turn it on. Yes, when you start to set the system, it seems like a little expensive than the others. But if you remember the life cycles of it, these systems are much cheaper than, and these systems give themselves back in energy savings to 10 years, between 2 and 10 years. Some countries started to support using shallow geothermal systems. As I know, they have some financial support to use and application these systems. Shallow geothermal system helps to reduce the greenhouse gas emissions up to 60%. And these systems are applicable for all the old and new buildings. So it's not too late if there's much old buildings in your country. So what's the advantage of thermally grouts, cement-based grouts? This type of grouts can be used with all the ground source heat pump systems and allow to reduce the pipe length. And they helps to energy saving and improve the performance of thermal pipes, because as we see in our Valencia application, we did some applications with using both thermal pipes and grout, and the grout and standard pipe. And we saw that if you use both of them together, your reducing coefficient is high than the others. The entire ground source heat pump system will be protected from underwater and ground sulfur attack. You can do it with just change the type of cement, and there's not big difference between the ordinary Portland cement or the sulfate resistant cement to use in your grounds. So if we need to hear current situation, for geothermal energy, overall installation growth is continuing at speedy pace. As you know, some crisis of energy and the lackness of the conventional fuels, all the world focused on the renewable energy systems. And the biggest renewable energy systems is the geothermal system for heating and cooling. This brought installed capacity up to at least 23,000 megawatt thermal by 2018, distributed over more than 2 million ground source heat pumps installations. And the all the sales about ground source heat pump systems in Europe total around 92,000, and the half of this number lead by Sweden and Germany. And the other companies start to use these systems. So for Turkey, this system started to use in beginning in the millennium, and for residential single-family houses with total capacity of 518 kilowatts. And now there is 146 application in Turkey, and their all capacity is 109 megawatts. And we know that these are still far away from the potential of Turkey. And I have to say that this system is really different from the standard geothermal energy, what we know from the literature. It's just shallow system, so you can apply it everywhere. So for the future of the SGS, geothermal market has grown for 8 years, and 25 gigawatt thermal installed overall for heating and cooling system, and nearly 2 million shallow geothermal system units installed. And there's also lots of fundings in it. So there's 36 European Union projects. One of them is GeoCont. And the all over the fundings is more than 300 million euro. And you can use these systems, hospitals, shopping malls, airports, your single house, schools, anywhere. So according to the plasma scenario, covering the required path to fulfill the 2030 target indicators requiring an average growth rate of the 18%. And this means 3 times of the current growth rate, according due to 2012. Within the direct installation sector of geothermal energy, the geothermal heat pumps have worldwide application, as shallow ground temperature is within their range anywhere in the world. So if you have some feasibility reports detailed about your thermal conductivity of ground and the climatic conditions and the building typologies, you can apply these systems everywhere. So this means it's the fact that this market has great potential. So there's lots of to do for shallow geothermal systems. Thanks for your attention. If there's question, I will be happy for answer it.
Thank you so much, Ms. Ayten, for your nice presentation, and then these are the valuable information for the market. Thank you again. When I look at the audience, maybe in the round table we will have some questions, so we can discuss on it. I will check the program now. We are on time, and Yusuf Hocam, if you want, we can proceed with Pınar Hoca. What do you prefer? And then,
Sure. I mean, just I was gonna criticize you. You gave very small, short time for the Punaroja talk, and I'm sure you will give us a good lecture in an hour. But I don't know whether we should give the break or just we will continue. I think we just have a break little while, so just we can start from now on with the Punarojam. But the problem is if anyone is looking for his talk and when they come, they will be late. I don't know.
yeah.
We can let Punaroja to decide to start or not. But I will be happy to listen him for long speech.
Thank you so much
And
for
not
your
only the
sizing. Yeah.
not only the 30 minutes, just
Yes, I know, Hocam,
Mr.
because
Punaroja.
due to the program, due to the number of the speakers, and then also we want to keep half day of this program. Sorry. Yeah, yes, we know our valuable speaker, Professor Menguç, and then we want to listen more, and then so I think we are on time, and then maybe he can also provide some insights and then feedbacks from this field, and then we can listen to him.
Sure. I mean, just Punarojam, is it okay for you to start?
Yes, I can start. Thank you very much.
Okay.
Thank you, Hocam. I appreciate your being.
I thank you, Yusuf Hocam, for invitation, for inviting me, and Burcu Hocam, I would like to thank you also. And it is really nice to be part of this workshop. It is not a small thing, and I was impressed with what you are doing as a group and as individual research groups. What I have been...
Hocam, maybe we just a minute, Burcu Hocam may introduce you to the audience first.
Yeah.
I know that many people know you, but it's a pleasure ourselves for introducing you again.
Okay,
with
thank
the audience whom do not know you. I know your research has been recognized from Turkey and even in the world, in the US, and you've been very prominent researcher. But Burcu, please.
Thank you, Hocam.
First of all, I would like to thank you, our invited speakers, for the acceptance to give a talk in our workshop. Professor Menguç received BS and MS degree from Middle East Technical University from Turkey, and then he continued his PhD studies in Purdue University in mechanical engineering department. Then now he is a professor at Özyeğin University, and also he is the director of the Center of Energy and Environment and Economy, and I think he's one of the leading persons and experienced persons in the field of energy, and we are really thankful for their for his valuable works in that field, and then we are really appreciated to listen to him now. Thank you so much for your participation. Floor is yours.
Thank you very much. Thank you very much again, Burcu Hocam. This is really an honor to be here. What I will do will be probably a little bit different than what you have listened this morning. I will give you a little bit a bigger view. Of course, your workshop should be related to the research that you are carrying under the project. But I would like to talk about what we have been doing. I came to, let me start my screen. I will talk about energy efficiency in general sense. I came to Özyeğin University about 11 years ago as one of the founding members of the university. I was responsible from establishing the mechanical engineering program. I noticed that many of you are also busy in the laboratories related to mechanical engineering, but also I am an energy engineer. my research is more in physics of energy. Over the years, I have worked on a number of disciplinary and multidisciplinary problems related to that. But the last 12 years, we started an interesting program on energy efficiency, especially for interdisciplinary and transdisciplinary subjects. So I will try to give you a view of this journey. It will be a fast forward in it. As I understand, I can talk a little bit more than 35 minutes. Is this correct, Burcu Hocam?
Yes, Hocam, we have more time.
Yeah.
Yeah.
Oh,
You have
then
more time.
if needed, I can.
Even 45 to.
Okay. I can stop and discuss some of the slides a little bit more. When I came to Turkey in 2009, there was nothing. We had nothing. And eventually we moved to our new campus in Çekmeköy, which is about 25 kilometers from the Bosphorus. If you think about it, just orient yourself from Bosphorus on. And we came out with one of the quite efficient, energy efficient campuses in the country. And just recently, we have published a book about what we have done. And this QR code will take you to the PDF of that book. For the moment, it is in Turkish, but within 2 weeks, we will have the English version of it. My research area is radiative transfer. I work on energy systems, I work on transport phenomena, and one of the books that I have been involved with in the last 12 years is Thermal Radiation Heat Transfer. A new edition just appeared a couple of weeks ago. And indeed, this book is interesting because the original authors, Siegel and Howell, have worked on Apollo and Gemini projects with NASA. So their radiation heat transfer book was basically to make sure that these spacecrafts, when they get back to the Earth, when they get into the atmosphere, they wouldn't burn. So radiative transfer is very important. And they are my father's age, both of them. Unfortunately, we lost Siegel a few years back. But they invited me to be part of their book. So in the last 12 years, I am collaborating with them. So you'll see my research will be more related to thermal systems and radiative transfer, but it's not enough. So what can we do about it? Well, basically, disciplinary work is when we are really good in our individual studies. Multidisciplinary work is when we begin to collaborate with other people. But usually in the multidisciplinary research, we do not learn other persons, other groups' work. We just collaborate, we tell them what we need, and they tell us what they can give us, so we can come out with new ideas. But when we get into interdisciplinary work, we begin to work with the other person. In it, we understand, for example, when you talk about phase change materials, for example, I need to pay attention to how you come out with these phase change materials from chemistry point of view. Then I can think about what it would require from physics and application point of view. Then I can get back to you. And if we begin to come out with a web of thought process like this, then we really produce something unusual. Indeed, the world has been working like this in the last 70, 80 years, and many of the cutting edge research came from interdisciplinary work. We have to do it. But then there's also transdisciplinary approach where sometimes we don't know what the solution is. The reason the solution is not clearly known is because there's human involvement. Like, we need to understand what humans need, their personalities require, and then based on that, what the society would take us to somewhere. Like climate change should be considered as a transdisciplinary work. There's not clearly a solution. So we cannot really solve a problem and come out with the answer and move to the next problem. But we have to develop the strategies towards better approaches. So that's what I will talk today. Coming back to climate change, and as I said, this is the radiator transfer, my research area. It's very easy to explain. I'm not going to dwell on the details too much because, you know, there's solar energy coming all the time. We lose some of the energy from Earth, and we have some reflection in the atmosphere from the Earth, and then there's some scattering and reflection from the atmosphere. Once you start changing the content, the constituents of the atmosphere by emitting more greenhouse gases, then you trap more energy in there. Then the trouble starts. Again, you all have seen these kind of problems over the years, but once we get into the details of the physical processes and chemical processes that take place there, it's extensive. It's not definitely done by only physicists, but it should be done by chemists. It should be done by biologists, and we should understand meteorological aspects, atmospheric effects, and on top of it, what we emit by producing energy on Earth that affects the atmosphere, we have to pay attention to that. In the last 50, 60 years, we added something else to it. As the cities became larger and larger, as we built more roads, more asphalt roads on the cities and so on, we started really having a different type of absorption on Earth, different type of reflection, and then we had the aerosols and pollutants emitted to the atmosphere, and all of these have additionally changed the balance of the atmosphere, and climate change was observed. Is this a new thing? Not at all. I can show you several other examples, but this is from October 2076, almost 45 years ago. Robert Sess is one of the radiation transfer persons, and he wrote about climate change, and he appraised the atmospheric feedback mechanism there. This is much recent. It's from 2017, written by James Hansen. James Hansen was the director of the Goddard Space Center at NASA. And if you just look at the title of this paper, it should really make you feel uneasy, because this is young people's burden. We are going to have a major problem for the young people, so we have to really get into the research, and we have to even reverse the carbon dioxide emissions. We have to have negative carbon dioxide emissions to change the things. And this is from Nature briefing that I just got yesterday. It's January 11th, that Arctic and Northern Siberia has about 3 degrees higher temperatures than their long-term averages. This shows that something is changing. I will not show you many things that you already know from other resources, but to be able to do that, we have to work together. And United Nations came out with Sustainable Development Goals. The bottom line on these is bringing humanity and nature to start working on these in a harmonious way. And again, just as of yesterday, Prince Charles of United Kingdom came out with the Terra Carta. I don't know if you have heard about this yet, but it is basically Sustainable Markets Initiative. From now, the companies, the corporations should take more responsibility for climate change issues, and hopefully there will be a bigger impact on the earth. And what you are doing in your project is indeed a very good example of what should be done for Terra Carta. There are some concerns about what Terra Carta means. Indeed, it comes from Magna Carta for human rights, but the Terra Carta may have some wrong implications, doesn't make any difference. There's a new push, new initiative, which will bring the companies and the researchers together. And Sabancı University, working with Sabancı Holding, is one of the prime examples of that. And Yusuf Hoca has been working on this for a long time as Dean of the Engineering, and then with the several research initiatives, including the center he's working on now. Okay, let's go back. What are we doing? What can we do? As you said, you work on a problem which will really help, but if we don't do anything with the current trends, we will continue releasing more carbon dioxide to the world. These will be in gigatons. And by 2050, we will see a linear increase. This is unavoidable. It's like population is increasing, everybody is using more, and then this will be the case. If we want to come out and really reduce this emission to 1/3 or so by 2050, we have to follow several sustainable development goals. This means that we must work on several different technical issues, from buildings, from light industry to power generation to biofuel transport, solar PVs, the wind, renewable energies, of course, fuels, carbon storage technologies, and so on. I will come back to this one. I will show you something very interesting next time when I show you this slide. But this slide is giving us the direction for future. All of us will be important because whatever we work, we will be working on different aspects of it. So we will reduce this trend line down to sustainable development line. With this, we established the center. We established the center about 11 years ago at Özyeğin University. Özyeğin University is really just 12 years old, 13 years old university. We moved to our campus only in 2011 at Çekmeköy at the end of 2011-2012. Then we established the center. Our objective was to really put nature and the climate change in the middle of it. This was our objective back in 2009, and then impact humans and society. Along the way, as you see in this spiral, we have several areas. Each one of these areas are indeed related to some of the important problems. In nanoscale and radiative transfer, we look at the energy harvesting and energy applications. Then we have building problems, as I will discuss a little bit more. Industrial applications we have, I will not discuss in this presentation, and cities we will not discuss. Then there's economical aspects and sustainable finance. I will show you a couple of slides related to that. All of these sub-areas were supported by different grants, several of them from Framework Program 7, and then from Horizon 2020. And we had several other grants from USA and from Turkish Science Council, from Islamic Development Bank, and several companies, including DHL, Bosch, Siemens, and so on. And during the process, I think we came out with a campus which is really, we are proud of, because it is using less energy than a typical university campus. And our center as a sustainable energy center has contributed to that. Back in 2011, there was nothing here, but now we have about a significant amount of solar power on the roofs, green roofs, and then architectural improvements on the buildings to save energy and so on. And this was not easy. We established a group, and we are working as a company. As a matter of fact, almost everything we do is coming from the projects that we are working on. But I think we were at the right place, and I think now your project is in very important place as well. Just recently, in September 2020, Nature Energy has published an opinion paper. by Asegun Henry from MIT, Ravi Prashar from Intel, Arun Majumdar from Stanford. Arun Majumdar was the director of ARPA-E for a long time, and now he's going to be in the Department of Energy under the Biden administration. They say that if we are going to do something for the future, we have to really look at the thermal energy grand challenges for decarbonization. They listed 5 important areas. The very first one is indeed your research area, which is very, very nice. So I'm so glad that I'm talking within your workshop when you are working on such a leading edge idea. There's decarbonization of the industrial processes. We have some projects on that. Cooling and heat pumping systems is also related to your work, as well as our cooling system applications. Variable conductance building envelopes is again phase change materials. This is also related to what you are doing. So in that sense, it is impressive. Probably you are not working on long distance transmission of heat, and we are not working. So in a sense that there is a chance that we can talk about these issues at intellectual level with many of you over the years. Our research, let me mention our research and how we really structured our center and where we are. So when we look at energy research in general, you can combine everything under 4 headings: energy generation, energy conservation, energy harvesting, and energy efficiency. Energy generation is a huge thing, from natural gas to petroleum to coal. I worked on this years ago, but now it's not our work. Energy conservation, as I will discuss, it's preliminary. It's relatively easy. And if you have any children in the middle school or even elementary school, they may teach you about energy conservation. Energy harvesting and energy efficiency are our objectives. Energy harvesting goes all the way to nanoscale. Energy efficiency can also go to nanoscale, but also it can go to buildings, industrial systems. It requires integration of architecture and engineering. It requires comfort. It requires sustainable finance. Energy harvesting, on the other hand, depends on the effective transfer of energy. Radiation transfer and near-field radiation transfer are important. So these are the areas that we can really take and apply to different parts of the industrial use. Good. But here, let's go to energy conservation and energy efficiency, which are the 2 most confused subjects. When we talk about energy conservation, indeed, we are talking about how little we use energy. It's indeed nothing but first law of thermodynamics. It's conservation of energy. In a sense, it is like the bookkeeping. It's like you keep following the money you have in your bank. So whatever comes in, whatever goes out, you balance it, and based on that, you decide to come out with the conservation. Yet, when you get into energy efficiency, first law is not enough. You must work with second law of thermodynamics as well. It is about quality of energy. It is not to cut the services. It is to increase the services, meanwhile to use new ideas, innovations, and new materials, new integration techniques, new strategies to decrease the use of energy density. Indeed, these 2 slides are not for you to read, but just to give you an idea of what I teach in my thermodynamics class. I really emphasize that this is the essence of the mechanical engineering. Indeed, this is like the Hippocrates oath of physicians in engineering, particularly in mechanical engineering. I make sure that students understand that they must consider energy efficiency, understand it, and incorporate first law and second law together to come out always with better design, coming out with better design to reduce the use of resources, energy, materials is the key for the future, for the impact of us to maybe not to solve, but at least to reduce the negative effects of the climate change. So energy efficiency is important. And when it comes there, I will introduce, I think many of you may know, entropy generation or versus exergy destruction. And if you work on this type of approach, then you may come out with better design. Well, this is good, but before you are able to come out with the second law analysis, you have to understand all other details related to engineering. So we have to come out with the interdisciplinary framework of integrated architecture and engineering if we deal with buildings. Buildings use about 40% of energy, which means if you improve them 10%, you will have 4% change in energy use in the world. That may be comparable in the order of magnitude of the solar energy use or wind energy use or geothermal energy use. Of course, we try to improve the solar energy use and wind energy use, but until that time, we have to reduce the energy density of the buildings. This requires architecture and engineering to be worked together. Now we are getting into that transdisciplinary part because we don't know how to do it. Yet, if you go 2,000 years ago, Vitruvius, my favorite architect, but if you read his book, he may be indeed a mechanical engineer or engineer, I shouldn't say just mechanical engineer, he may be a material science scientist. He was an opticist. He came out with lots of ideas 2,000 years ago to come out with the better living conditions. Better living conditions mean that at the end of the day, when you move to your new office, your new house, only thing you want to have is comfort, and you don't want to spend a lot of money on energy. So given that, we have to look at these things. But to be able to do that, we have to go and look at what we are doing as engineers and what architects do as architecture. And we have to combine them. Well, if we start from fundamentals, let's go to disciplinary work. Disciplinary work, what are these? These are Maxwell's equations, radiative transfer equation, Navier-Stokes equations, computational fluid dynamics or computational heat transfer or quantum mechanics. There's no need for me to write the equations here, just the names. But if they are used for a building, and as you showed in your project, indeed you are close to all of these subject areas, and you, I'm sure, phase change materials will go to quantum mechanics eventually. But the people outside see only function, comfort, energy efficiency, aesthetics, and ethics. So indeed, what you are doing here is just something to be hidden for these outside scale-up concepts. Especially comfort and energy efficiency were our initial goals. And with this, we got a Need for Me project. This is from FP7. This was close to $1 million to our center, but we came out with the most energy efficient building in Turkey. Right outside, do you see this picture? Right outside, in front of this building, we have a heat pump, ground source heat pump, which helped the building to approach these very low energy density. 44 kilowatt hour per meter square year needs to be compared against the 255 kilowatt hour per meter square per year in a typical Turkish academic building. Indeed, we built this, and then recently we made measurements. We went to energy monitoring systems and took the snapshots that you see here. And our Scholar building is just here, this, not the orange one, this arrow mist, this pink one, the small pink one here, compared to the AB1 academic building one, which is our best building in the campus. It uses almost 1/3 of the energy. So if we didn't do anything about this, the architects of the university would have built it similar to AB1 because it is, again, our best building. The difference between this design and the Scholar design gives us about $200,000 less energy use a year. But there's another important thing about this 200,000, if you think about in a different way. This $200,000 or the amount of energy we don't use in this building is equivalent to amount of solar energy we collect on 5 buildings in the university campus buildings. So indeed, by just using combined integrated work, and of course with some investment, we really came out equivalent energy generation from entire solar panels in the campus. So this gave us a lot of good feelings because this means that we are really coming out with energy efficient building. And indeed, one of our recent papers showed that the second law of thermodynamics was used significantly here. We got several awards for this building. We got the first place from the Ministry of Industry and Technology last year, and from also a few other organizations. So we are proud of that one. We have another research project which we completed. It's a breaker. In both projects, by the way, we work with Spanish partners. We work with Circe in Zaragoza. And this time we applied this to another campus, Adnan Menderes University campus. We came out with concentrating solar power systems, not the PV systems. As you see, this is the field. It's almost equivalent to 2 football fields. And there are some issues in operation of this, but we are coming too close to that. Our expectations is the savings for that medical school building per year can be close to $500,000 a year. They pay themselves within a few years. But on the other hand, as I mentioned, we have to go to the energy efficiency for humans. We have to look at also human building interactions. It's not just engineering. This means we have to look at the culture, how people behave. For that, transdisciplinary work is essential. So then let's go there. We have to consider all these areas in tandem. When you talk about thermal comfort, I'm just going to show you, not to discuss. If you read a couple of these things, you will never agree with your friend or with your wife or husband that one of them is the most important in your living quarters, in your office, and so on. So indeed, there are several approaches. This is complex, but this has to be customized. So it means I cannot really, as an engineer, come out and dictate that you will be most comfortable in this temperature, at this temperature, or at this light conditions, and so on. So we got another grant from Horizon 2020. Indeed, this was the first grant that came to Turkey at that time. Again, this was with our Spanish colleagues, and there were a number of other people, including French, Italian, and so on, and Swedish. We tried to come out with a new gamification that was to change people's habits, make them feel what they are feeling, so then they can really express it using their smartphones. And then this is basically our general project, a general concept. Once we have this, we can really combine all of these, from clothing sensors to HVAC systems to smartphone cameras, and well, and this was drawing by Ebru Tatar and Elif Tunçal. They got their master's degrees last year, but they applied to a competition by Schneider. Out of 19,000 applicants, 24 people were selected. They were among those 24, and they got an award. There, they worked on their master thesis in the center, but their approach was more general. Indeed, Ebru worked on clothing, and Elif worked on heart rate, body temperature, skin conditions as a function of the conditions that we can change in a room. So somehow you have to combine all these things. Combination of all these things is not that easy. This means we have to work on the Internet of Things, wearable technologies, building systems, mood sensing technologies, and so on. This brings us to this slide again. Now I would like to mention, just look at this small, the second to the last entry that was entered by international energy agencies. This is behavioral change. Look at this dark red box. It is comparable to wind or solar PV or biofuels transport lines. So International Energy Agency clearly shows that the behavioral change will be as important as solar PV, wind, and so on. And when was this published? Right here, right here. So we are right here. So behavioral change is understood now at this point. So we hope that we are going to make a big impact on this. Indeed, back in 2017, there was this Science article showed that at that time, the behavioral interventions in the United States is savings about $2 billion over the time. Well, if you are in Istanbul, you know that the cats of Istanbul know this very well. They know the best places to feel comfortable and efficient. We wrote a paper with Cem Keskin. Since then, he got his PhD in the center. We talked about how we can really combine technology, behavior, and complexity. It was published in Sustainability. And indeed, there was a major research review that combined behavior, thermal comfort, Internet of Things, innovation, technological change or technology resistance, technology adaptation, and how you come out with behavioral change. All of these need to be considered. Just imagine, if we are just working in our disciplines, we cannot really approach to this problem. This means we have to work in big groups. We have to understand each other. If we just combine, then we see that behavior studies, healthy indoor environment, building physics, and cyber technologies are all part of it. Note that healthy indoor environment due to COVID has become bigger deal now than ever before. And I'm not going to get into details, but there are several theories that you need to really couple them so you can bring your friends from psychology, sociology, electrical engineering, computer science, industrial engineering, all of them together, combine all of them and relate the energy sciences to sustainability sciences along with several other very well-known areas. This will bring us to the socio-technical core that human factor and building systems are explored together. Well, let's go back now a step to our disciplinary areas. To be able to do that, you have to work on the computational fluid dynamics. How does drift or effect of HVAC system in a room or in an auditorium affect individual students? This was from several years ago, and several students really worked on different aspects of this problem. And as you can imagine, with COVID, something like that became bigger deal. And indeed, we did an extensive COVID study in the campus. We looked at more than 1,000 locations in the campus and figured out how long a infected person start infecting other students in the room. But this was an afterthought of this. We also need to work on the mechanical engineering of it. One question is this, and if you are in your office now, look up to the ceiling and you'll see these type of fans, air diffusers. Ask yourself, why do you need them? Why? What's the reason that they are there? And once you begin to ask that, indeed, engineers and architects really worked in their disciplinary areas and never asked that question, whether these will be good for the entire room. So we came out with one of the living laboratories of student offices, and we put there several different thermal agents, and then looked at the different way of diffusing the air into that, and then came out with new type of diffusers, which are adaptive systems, which we applied for a patent. And then depending on the location where you live, we began to measure 2 degrees. This was preliminary results. And then extensive studies with CFD show that depending on your design, we can really affect the room and come out with significantly different temperature difference at different locations. You know, reducing temperature by 2 degrees in a room make you save about 10% of energy. This is known. But you don't want to change everything by 2 degrees. So what we are showing here, depending on how you use your room or office space, you can really affect only certain areas and not other areas. If that's the case, you can really achieve more than 10% improvement. Now, this is critical, as with the COVID, you don't really get close to other people. When we started working on this research, one of the criticism we got from a few people, well, once you have 2 people side by side, how are you control their desires? Well, the answer we had for them was, look at the expensive cars. Look at a Mercedes. They can control, for example, right seat from left seat air conditioning system. So we can do it. But now with the COVID, people are not that close to each other anymore. So this means that this application will save close to 10%. This is the disruptive approach to HVAC system in the world. But what else we are doing? Some of the, I will finish in few minutes, but we have to understand also the materials. Now this goes directly to what you are doing. So we need to look at how and why we need to develop new materials. We work on biologically inspired near-field radiative transfer to come out with sensors, although I'm not talking about that. I'll a little bit talk about radiative cooling related to buildings, although with Sabancı University and Boğaziçi University, we worked on the near-field or nanoscale radiative cooling modalities as well. Think about the buildings, especially in southern Spain or southern Turkey or anywhere in the world during the summer. Buildings are scorched by sun, and then you use air conditioners. Air conditioner is the biggest concerns for energy use in the world. And air conditioners became more common, and they are really sucking up all the energy during the summer months. So just imagine like a Jules Verne or so. What if this building cools off when sun is instant on it? Doesn't it make sense? Well, this idea, we started working on this about 10 years ago, but last 2, 3 years, this became one of the biggest research areas in the world. For a passive cooling of buildings, there are many, many approaches. And of course, phase change materials is one of them in the wall boards, ceilings, roofs, and so on. They are all written one way or other. But then also heat dissipation techniques should be considered, and radiative cooling and new paints will be the part of it. Your passive cooling approaches will be the future paints. So in that sense, I am really excited about the research that you are working as a group. But when we go to radiative cooling, now we have to go to spectroscopy, which is an area that's not very well known in mechanical engineering, for example. In material science, it is known. In electrical engineering, is known. In mechanical engineering, it's not usually known. The idea here is when we have the energy coming from sun, we get it here. So somehow our building paint should emit more at the atmospheric window rather than at the solar spectrum. So if we can come out with a new technique which emits, well, absorbs less, therefore it emits less in this spectrum and emits more in this spectrum, we can really come out with much better conditioning of the building exteriors. We worked on a number of different problems, and I would like to leave it to you, and maybe we can work on some of them. We definitely worked on perlite, pumice, cement composite materials, and they can be used for bioinsulation. We looked at painted and coated bioinsulation panel, and there are other panels which are used in the literature or in the applications, although their work is not well understood. Again, our goal is, as humanity, to impact the world so we can really make a dent on the problems of the climate change. UN Sustainable Development Goals list several of them, 17 of them. And as a center, we really worked on 7 of them. We applied our know-how to 7 of them, although 7 and 13 are primary goals. But what we found out that I think these sustainable development goals will not be sufficient. Because of this, 2 years ago, in one of the conferences, we proposed indeed that there should be an 18th goal, and it should relate to culture. Many of these goals include cultural aspects, but there should be a significant impact to culture and transdisciplinary work if we are going to make a significant impact to climate change. So with this, we also emphasize education problems and education projects. And one of the projects that we got was from Islamic Development Bank. Islamic Development Bank established a major fund some time ago based in London. And we were the first one in Turkey who got a significant grant from them. Our objective was to go to southeastern Turkey and work at 10 vocational high schools at 10 different provinces. It worked very well. In the beginning of 2020, we got an award from EEE in Kochi, India. We applied a similar concept to Çekmeköy, but in these 2 areas, we had significant impact. We have a very detailed video of it. I'm not going to show you, but if you use this QR code with your cell phone at some time at your leisure, you can see what we have been doing. We are very proud of it because this is relatively less fortunate, economically less fortunate area. We brought the state-of-the-art knowledge and engineering there, and we changed 10 schools. We implemented energy efficient systems there and measurement systems, and students were really happy. Unfortunately, COVID came, and the last 11 months, we were doing it from distance. With this, I would like to stop. As I mentioned, this Nano to Giga, from Nano to Giga book is to summarize our work in the last 11 years. This QR code will take you to the PDF of this book. The Nano is, we do some nano work from bio-inspired near-field radiation, so on, and Giga refers to, hopefully, gigatons of carbon dioxide we save in the process. With this, I would like to stop and ask if you have any questions.
Pınar Hocam, thank you very much. This is very great talk. That we listen. It is really pleasure for us, and we learn many things, and then we understand the importance of the energy efficiency, and especially by taking into consideration recent trends. Thank you. Maybe we can. Thank you. If audience have question, we can take it. And also we our groups we can ask question and then continue with some round table and then discuss the emerging technologies in the recent trends.
I might start with the one question to Pınar Hocam. Just saving on the buildings, you mentioned that $200,000, it's a huge money. And you're saying that the building cost is a $1 million and the saving in a year in 200,000 is a good match. Huh? Just on the 5 years, you just recover your cost of the building. Did I understand correctly?
Well, this building is a huge building. It's a 17,000 square meter. So the cost is about 5 million.
Okay.
But think about this: the cost of building, the operation of the building. If you save $200,000 a year, the operation of the building is say 50 years. After 50 years, building can be changed or significantly modified. The amount of money you save is definitely twice the cost of the building. So it is huge. As far as the investment and return on investment is concerned, it's about 3 years. So the building is going to be built, but the improvements and savings take care of it within 3 years. Another important thing, though, this shows that we must work with architects. Otherwise, I think it's a good idea to get the solar energy, solar PV panels everywhere. They are nice, but most of the time we are paying money to other countries for these solar panels. Until we build them completely in Turkey, we are giving money to outside. By combining architecture and engineering and coming out with new ideas there, we save. So this is, we call it negawatts. Negawatts is referred to megawatts. Negawatts is negative watts that you can really reduce in energy use.
Hocam, also I would like to ask for your comments. I have a journal from SAMPE. SAMPE is the committee and educate the members on emerging technologies, and then they list up some technologies and then address some emerging technologies. I would like to mention these technologies. One of them, automated manufacturing processes, energy storage technology, hydrogen technology, hypersonics, modeling simulation technologies, recycling technologies, electric vehicles, Internet of Things, Factory of the Future 4.0, sustainability, urban air mobility. Yeah, you mentioned most of them, and when you look at these emerging technologies, can you what do you see in Turkey, and then when you align these technologies with the Europe and world, and then Turkey and which technologies should we focus on more, and then should we catch up this world?
Burcu Hocam, thank you for this question. Indeed, this is really a crux of the matter. Easy answer. We must focus on all of them. But I think the real value will be getting these technologies and being experts on on many of them, and then coming out with layers of the research areas, layers of the research programs, the centers and intra-centers, centers that combine many centers in Turkey, as well as in Europe, in the United States, in China, and so on. The idea is this: our brain needs to be focused, needs to be very good in that discipline, a single discipline. We must have a good feeling, intuition of what we are doing. But then we must also have a larger view of where it can be applied. Yet we cannot be an expert on that field as well. We can be expert on 3-4 fields, but the world is way more complex, as you have seen in a couple of slides that I showed. We must combine several things. So it means that after we become very good in our areas, we must work within the centers, within the intra-centers, to apply those areas specifically to different problems. There, for example, I'll tell you one thing, that in the beginning of last week, I attended a National Science Foundation workshop about several agencies in the United States. They are trying to come out with new projects. And specifically what they say is this: there's no money problem. There's no funding problem. The problem is innovative ideas. And innovative ideas is usually not the same thing that you are doing and repeating again, but taking whatever you are doing, combining it with another discipline, chemistry, physics, psychology, earth sciences, political sciences, whatever, and coming out with something that's going to have a bigger impact. Before continuing too much, I will emphasize, I think that I need to focus all of us to two things. These two questions are asked by the National Science Foundation in the United States to every proposal writer. What is the intellectual merit of your project? What is the broader impact of your project? Two questions. Intellectual merit is, we must know what we are doing very well. We must be an expert in our own realm. And the broader impact, how we can take this idea and apply all the way to the community at large, to the society. Just an example, this evening, if you are watching the news, they will tell you something, that all the COVID vaccinations have been produced, and in the United States, they are not able to vaccinate people. So indeed, the transfer of all these vaccine to the society is missing. So there, for example, a big need for industrial engineers to start with, or big trucks or whatever. So completely different than the vaccine itself. So you see this kind of transdisciplinary work where people's unknowns, people-based uncertainties surface up, and then you miss the broader impact, is the major problem. So because of this, I really urge, this was a great thing in it. I would like to thank to Yusuf Hocam and to you for invitation. I think this is a very interesting way of bringing two centers together to think about what can be done. because I think our strengths, different strengths, can allow us to come up with solutions to bigger problems. So that's what I would like to say. None of them is less important. It's important to find somebody who is really excited about any of these areas and learn it in depth.
Okay, thank you. We should work hard, I think, to catch up all the technologies and then provide more money and then to continue our research.
Can I add some comments about this answer?
Yes, yes, please.
Well, I don't know if Professor Pina is also agree with that, but in somehow this kind of reflection is now reflected in the current call in the European proposal. You know, in the for example in the Green Deal project, call for project, they are insisting a lot in the social version of all these projects, even in the research, innovation, and actions. No? So they really want to connect, and the projects are getting bigger. You know, there are not so many projects, but the projects that are funded are big projects with a lot of connection between different science fields. This is also a social aspect is critical, social economical aspects. So we consider more now because of, I don't know if this is also affecting to Turkey, but you know that Spain is receiving now all this funding for COVID from Europe. Well, Spain, all the European countries are receiving funds from the central bank, and all these projects that are applying for these funds has to consider always the social aspect of the not only solutions, but social changing behavior of the people, and especially in the industry, because people can change the mind more or less, but change the industry means also some technological changes, new equipment, new evolution in the apparatus, etc. That the company, they are not always tackling very happy. so it's very important. I don't know if he agree with this comment. And also in about your question, I can tell you a little bit about the Spanish version now that is regarding the new energies concept. No, so obviously we know a lot about geothermal, and geothermal is considered very important for the district heating and storage. Storage of energy is becoming more important than producing of renewable energy, because they know that with the current technology of wind, solar panel, PV panel, etc., they are able to produce a lot of renewable energy. The problem is how to store this energy. So they are trying to make an evolution in this kind of storage technology, because battery is limited, it's a limited aspect, but thermal storage is considered quite important. And in Spain, they say that the energy vector for storage energy would be the hydrogen technology. So all the seeds of energy produced by wind, by solar, or whatever, during moment that they cannot be used, will be used to produce hydrogen, blue hydrogen. This is the current trend for the next 10 years, at least in Spain. And the company that we are advising some industrial association, for instance, from the ceramic sector that is consuming a lot of energy, and then their advising is always that they need to incorporate hydrogen as a potential fuel for the oven processes and so on. So this is only the comment that I wanted to do. For me, I would like to thank also Professor, because the talk was very interesting.
Thank you, Dr. Castle. I have to tell the first part of your question, that social aspects become important. It's not only in Europe, it's in the United States as well, especially in California. This has been being pushed for the last 4 or 5 years. So behavioral energy is not something that I just came out with, but we have been working on behavioral energy for 5, 6 years. We started about the same time that California started. I think this will become important, because without really considering the individual, customized, adaptable impact to the individual humans, individual beings, then your work will be lost. And I think in the long run, within 10 years, we'll see many startups, new companies working on the social aspect, which will be good for the earth. Otherwise, we cannot do anything about it. And it is Terra Carta concept that was just yesterday explained by the Prince Charles. Not that Prince Charles is a scientist to be able to comment on that, but I imagine there's a group of people behind him pushing these ideas. And it is very good because the companies will be paying more attention, and companies pay to social aspects more than university professors. So this is the time to combine these. As far as the hydrogen is concerned, I am completely in agreement with you. Just a few days ago, we discussed this again with a very dear colleague of mine, and these will be the future approaches, because many other things are well known and there will be incremental improvements on the other areas, but in hydrogen we are looking for really leapfrog improvements. And I think hydrogen will be significant for thermal storage. And again, sending heat to distance. This is another thing. You have to store and then you have to take it to somewhere else. This will take us back to the Carnot cycle.
This is the main challenge.
Thermodynamics. Whenever you have two resources which are significant at two different temperatures, then you can really produce electricity out of that. It's a very simple thing. It's 200 years old. Carmel lived in 1820. So, but the idea, the basic principle is there, and the devil is in details.
Burcu, can I ask?
Yes, please.
I have a very specific question, much more specific than previous ones. It is concerned with using phase change materials in construction, in buildings. We can see from scientific literature that I would divide this subject into two. So incorporation of phase change materials in building envelope, so walls, ceilings, and the using of phase change material in energy systems of buildings, like hot water systems, heating, cooling, and so on. It seems that from economical point of view, it is much more probability of viability of using phase change materials in energy systems of buildings, and less probability of using it as a part of construction materials, of building materials, because of cost or maybe even not enough technical performance. Could you please comment on this?
Sure.
Potential.
Let me take back and let me give a historical background first and then come to a specific question. I think in human civilization, one of the biggest discoveries is the refrigeration systems. Refrigeration, cooling something, is something that's not available in the nature. And humans came out with the refrigeration systems. Indeed, a refrigerator is two cascaded heating systems. To be able to make the refrigeration work, you need a refrigeration fluid, a specific refrigeration fluid. And you know that original refrigeration fluid that was used in 1800s or 1900s caused all the ozone problems on Earth and so on. But indeed, it was the discovery of the refrigeration fluid that allowed us to come out with the two cascaded heating systems, which allowed us to come out with the refrigeration concept or air conditioning system. The reason I mention this is I think we are facing a similar extraordinary change of thinking now. Of course, it's not parallel, it should be different. Phase change material idea is a great idea to make use in building facades. So we know that it's a very good idea. We also know that phase change materials as of now are very expensive, so nobody can really apply them to building materials. And to be able to have a significant impact on buildings, the bottom line is we must have dirt cheap materials. So your phase change materials, if they become dirt cheap, the impact will be larger. So the challenge to material scientists is to come out with the dirt cheap phase change additives. And I don't know the solution, by the way. This is something that's not yet found.
Okay, and what about chances of integrating phase change materials, let's say in hot water systems, or to combine it with photovoltaic panels? We see a lot of scientific literature and activity about this applications, the specific applications for phase change materials. It seems, at least, that there are no such strict limits on price of this material to be implemented in these applications, in contrast to the implementation within the construction materials.
As you said, there are some potential applications, and they are niche applications, but that goes directly to the economy, and somebody tries to justify whether adding another cent of cost is a good idea for the competitiveness of that company. So it's a business plan. I think this is, at this point, it's business plan. But from my point of view, I tell you my feeling. Phase change material, I follow BASF quite closely, and you know, BASF had these phase change materials for a long time.
With Micronal, yes.
Yeah.
They have sold this business, by the way,
okay.
to Microtech.
Yeah. But I could not bring myself, for example, in our application building to use the phase change materials because they were expensive. My objective is to make sure that whatever I use has significant, widespread use. And because of this, I didn't get into the phase change material concept, although it's really the thermodynamics, and what you are showing in your slides and in your video was very, very impressive. The question is, are there other materials that allow you that phase change at atmospheric temperature and pressure? Is it possible to use nanocapsulated phase change materials which may be readily available in the literature and mix it with cement or just apply it to a paint on the surface? I don't know. But these are really beautiful research questions because they allow you to imagine.
We are working on this.
If I can add a comment, I mean, I know that the interest in the phase change material in Europe, especially with regarding the storage, as I said before, in the storage for thermal energy is huge at the moment, you know, huge. I saw several proposals that there are people are preparing. We are trying to apply also to some proposals, and all the people are considering not only phase change material, but phase change material is always considered as one of the technology that has to be studied in some part. You know, there are several groups, like I don't know, but there are people in Germany that are very strong in the phase change material. The Fraunhofer Institute in Germany is working very, very hardly. And they are also in Delft University group dedicated and devoted to that. And not only with this, that I was surprised, but also with the food technology, you know, because they are very, very important for food technology, for the transport of food. And they,
transport, yes,
yeah.
cold chain, yes, that's right.
And then now with the COVID, you need the special condition for these vaccines, and then they are talking again about the phase change material that could be applied for that. But I told you, I think in the discussion in the project, and several times we talk about that, I think that the price of the phase change material could be drastically reduced if we find a mass use of an application for mass use of this PCM, because in fact, there are fatty oils and something like that they are expensive because we are almost producing for for laboratory techniques, you know. I remember when I was talking with the people in Repsol or in the Repsol company, you remember that, and they told me that if we don't have a very specific condition, like if we don't have something like we need a PCM that is melting at 26 degrees and something like that, if we are okay with a range between 24 and 30, it's okay for us. The price can be reduced by how to say, by 10 times, you know, 10 or 12 times.
Order of magnitude.
Exactly, order of magnitude. So I guess that in the moment that the technology could prove valid use for this phase change material, and especially considering this biological aspect or biological, I mean the data sheet, the danger data sheet of the phase change materials changed a little bit, that the people are not so afraid about that. I think that the application will be fine for sure.
Okay.
Mm-hmm.
I agree.
I'm very optimistic about that.
Okay. Is there any question or comment? Then I will close the workshop, and then thank you for your participation and then valuable speeches. Maybe we can take a picture. Yeah, if we make a face-to-face meeting, and then we can go pictures. But now just only we have screenshot. Just I will. Maybe we can, if the audience turn on the cameras, and then we can take.
But you you did a great job with this. Very nice workshop.
Thank you so much. And then say cheese. Yeah, just screenshot. Okay. Thank you so much, Pınar Hocam.
Thank you all.
We are really,
Thank you very much.
a pleasure for us, and then Michael and Jose, Ayten. Thank you so much.
Nice to see you again.
Nice to see you.
Thank you.
Pandemic, we will see each other again. Thank you
we
so
will
much.
miss.
Yeah.
We miss each other. Thank you very much for this great project. Thanks a lot.
Thank you.
Maybe in
Thank
another
you.
project
Have a
we will
good
meet
day.
again.
Thank you.
Yes, it will be great,
After
Michael.
COVID.
After COVID.
Bye bye.
Bye bye.
See ya.
Teşekkürler Pınar Hocam.
Sağ olun. Teşekkür ederim.
Görüşmek üzere. Thank you again for all participating. Thank you. Now I'm stopping the recording.
Yes, I'm
Ne aldım?
okay. Thank
Okay.
you.
Bye.